Let us continue our analysis on planar dielectric optical waveguides. If you remember that we were doing the analysis for confinement in x direction and propagation in z direction, and we had seen that if the confinement is in x direction and the propagation is in z direction, then the electric and magnetic fields associated with the light wave can be given as E x y z t. In fact, here you need not to take y because I am taking the planar waveguide. So it is simply E x z t E vector is equal to, now it is E0 or E of x e to the power I omega t minus beta z. Similarly, H is x z t is equal to H of x, this is H of x e to the power I omega t minus beta z. So, they represent the modes, E of x and H of x, and we know that since this is propagating in z direction, then what we have is basically E x, E y, E z, all these components will be there, and H x, H y, H z, all these components of E and H would be there. This is a mode propagating in z direction, and you should remember that these E and H are not constant. So, these are not plane waves, that is why I will have all the components here. Okay. What I want to find out now is what are the values of beta and what are the corresponding E and H. They define the modes, and we were doing the analysis of this. We were doing the analysis for symmetric step index planar waveguide, where this n of x is defined like this, and this waveguide is symmetric about x is equal to 0. It has high refractive index region n1 and low refractive index regions n2, and the width of the high index region is d. So, what we did, we categorized the modes of this waveguide using the symmetry of the structure into symmetric and anti-symmetric modes, and for symmetric modes the field, the electric field, we were doing the analysis of TE modes. So, for TE modes the field is given by this A cosine kappa x for mod x less than d by 2, that is in the guiding film, and C e to the power minus gamma mod x for mod x greater than d by 2, which is in these two regions. Okay. Since it is TE mode, so the non-vanishing components of E and H are E y, H x and H z, and E y, H x and H z are related by these three equations. So, we applied the boundary conditions at the interfaces x is equal to plus minus d by 2, and the boundary conditions are the tangential components of E and H should be continuous at x is equal to plus minus d by 2, and the tangential components at x is equal to constant are E y and H z. So, and since H z is related to E y as some constant d E y over dx, that is why E y and d E y over dx should be continuous at x is equal to plus minus d by 2. So, when we applied this, then we got the transcendental equation kappa d by 2 tan kappa d by 2 is equal to gamma d by 2. Now our task is to solve this equation. Okay, let us see how we can solve this equation and get physical insight into the modes of a waveguide. So to do that, what we do is we take this transcendental equation kappa d by 2 tan kappa d by 2 is equal to gamma d by 2, and here we see there are two terms appearing which contain kappa d by 2 and gamma d by 2, where kappa square is given by this and gamma square is given by this. So if I add these two up, kappa d by 2 square plus gamma d by 2 square, then I get k naught square n1 square minus n2 square times d by 2 square. What does it have? It has all the waveguide parameters and the wavelength, because k naught is 2 pi over lambda naught. So by adding these two up, I get something which contains only the waveguide parameters and the wavelength, which are the inputs basically. So let me define this, since everywhere there is a square. So let me define this as v square, and where v is k naught d by 2 is square root of n1 square minus n2 square, or 2 pi over lambda naught times d by 2 is square root of n1 square minus n2 square, and this I call normalized frequency because it contains lambda in the denominator. So I call this normalized frequency, or generally I also call it V parameter. Okay. So now in order to solve the transcendental equation graphically, what I do, I define this kappa d by 2 as some parameter xi, okay, some variable xi, because this is the transcendental equation in beta. Kappa contains beta, okay, the only unknown here is beta. So let me define kappa d by 2 is equal to xi, and therefore if I put this kappa d by 2 is equal to xi here, then gamma d by 2 automatically becomes square root of v square minus xi square. So if I put these two here in this equation, then the transcendental equation becomes xi tan xi is equal to v square minus xi square's square root. So in this equation I have all the input parameters in the form of v. So if I have all the waveguide parameters with me, that is n1, n2 and d, and I have the wavelength at which I am operating my waveguide, then I can calculate v from here, and for that value of v I can solve this transcendental equation and get the values of xi and hence the values of beta. Similarly, if I do the analysis for anti-symmetric modes in the same way, then it leads to the transcendental equation, which is given by minus xi cot xi is equal to square root of v square minus xi square. So the guided modes of a planar waveguide, whether symmetric or anti-symmetric, they fall in the range of n effective lying from n2 to n1, and they are given by Ey of x is equal to a cosine kappa x for mod x less than d by 2, and c to the power minus gamma x for mod x greater than d by 2 for symmetric modes. This is the symmetric solution, and the values of beta which are allowed are given by xi tan xi is equal to square root of v square minus xi square. So these are symmetric modes, and similarly the anti-symmetric modes satisfy the equation minus xi cot xi is equal to square root of v square minus xi square, and the modal field is given by in terms of sine function sine kappa x in the guiding film, and again exponentially decaying function in in the N2 region or lower index surrounding. So, by solving these equations, first I need to get the values of beta. Only certain values of beta or certain values of xi are allowed. I first need to find out those values of beta, and from those values of beta I can find out kappa and gamma. Okay. Those values I put here in the field, and then I get the modal field. That is how I will get the complete solution for the modes of planar dielectric waveguide. So, let us solve it. So, I have again symmetric modes, anti-symmetric modes. In order to solve these two equations, what I do, I equate both the LHS and RHS of these equations to some variable eta. So, in this way I will have sets of two simultaneous equations for symmetric modes as well as for anti-symmetric modes, and these are eta is equal to xi tan xi from here, and if I equate this to eta, then it gives me xi square plus eta square is equal to v square. These two equations are for symmetric modes, and similarly for anti-symmetric modes I get the equations eta is equal to minus xi cot xi and xi square plus eta square is equal to v square. Now, I can obtain the solutions of these equations by graphical method. So, what I need to do, I just plot these two equations on xi eta plane and look for the points of intersection. Those point of intersection will give me the values, allowed values of xi, and hence the allowed values of beta. Okay, so let us plot these. So, here the red line shows the equation eta is equal to xi tan xi, which corresponds to symmetric modes, and these blue lines, they show the plot for eta is equal to minus xi cot xi, they correspond to anti-symmetric modes, and these circles for different values of v are basically xi square plus eta square is equal to v square. So, for a given v, for a given value of v, I take these circles and see the points of intersections of these circles with these blue and red curves, and they will give me the allowed values of xi. Okay. So, let us examine these. So, V is this. So, for a given waveguide, that is n1, n2 and d, and given wavelength, that is lambda or lambda naught, V is known. If this V lies between 0 and pi by 2, if this V lies between 0 and pi by 2, we can see that there would only be one point of intersection, and that would be with the red curve, that is corresponding to symmetric modes. So, this point of intersection will give me the value of xi for this symmetric mode. So, in this range, if V lies in the range 0 to pi by 2, then there is only one mode which is possible, and this mode is symmetric mode, because it is obtained from the intersection of red curve with the circle, and red curve corresponds to symmetric modes. Now, if V lies between pi by 2 and pi, for example, if V is equal to 2.5, I see two points of intersection, one is with red and one is with blue. So, one is with symmetric and another is with anti-symmetric. So, I get two modes, one symmetric and one anti-symmetric. Then if I look in the range pi to 3 pi by 2, if V lies from pi to 3 pi by 2, for example, V is equal to 4, then I get two symmetric modes and one anti-symmetric mode. Okay. So, in this way, for any given value of V, I can find out the number of modes, the number of symmetric modes, the number of anti-symmetric modes, and their propagation constants. So, in general the number of guided modes I can find by looking at the value of V. If V lies between m pi and m plus half pi, where m is an integer 0, 1, 2 and so on, then I will get m plus 1 symmetric modes and m anti-symmetric modes. On the other hand, if V lies between m plus half pi and m plus 1 pi, then I will get m plus 1 symmetric modes and m plus 1 anti-symmetric modes. In general, I can get the modes for any value of V, and I label these modes as TEM mode, okay, where m is equal to 0, 1, 2 and so on. So, the very first mode is TE0 mode, then there is TE1, TE2, TE3 and so on. So, that is how the modes are labeled. Now, the number of modes I can also find out by looking them at V line. So, if I have V line and I divide it into the sections of pi by 2, then what I see that from 0 to pi by 2 there would be T0 mode. If V lies somewhere here, then T0 and T1, if V lies somewhere here, then T0, T1, T2 and so on. So, every pi by 2 I am adding one mode. So, in general if I know the value of V, then the total number of modes can be found out by dividing this V by pi by 2. So, I divide this V by pi by 2 and get a number, then the number of modes would be an integer closest to but greater than that number, closest to but greater than that number. So, if this V over pi by 2 comes out to be 2.1, then the number of modes would be 3. So, what is a single mode waveguide? If V lies between 0 and pi by 2, that is V is less than pi by 2, then there is only one mode supported, that is TE0 mode, and this TE0 mode is the fundamental mode of the waveguide. Okay. I give you an example. If N1 is equal to 1.5, N2 is equal to 1.48 and D is equal to 3, okay, then this waveguide can be single moded or multi-moded. It depends upon the wavelength I am using, because V contains wavelength also apart from these three parameters. So, by just looking at waveguide parameters, I cannot say whether the waveguide is single moded or multi-moded. I will have to say it is single moded at this wavelength, or it is single moded in this range of wavelengths. So, I can find out that range. I know that V is equal to 2 pi over lambda naught times D by 2 times the square root of N1 square minus N2 square, and if V is less than pi by 2, then the waveguide is single moded. Then this gives me that for these parameters of waveguide, if lambda naught is greater than 1.46 micrometer, then the waveguide is single moded. That is, for all the wavelengths longer than 1.46 micrometer, the waveguide is single moded, and for all the wavelengths which are smaller than 1.46 micrometer, the waveguide is multi-moded. For all the wavelengths shorter than 1.46 micrometer, the waveguide is multi-moded. Let us do few more examples. So, let us consider a dielectric step index symmetric planar waveguide with N1 is equal to 1.5, N2 is equal to 1.46 and D is equal to 4 micrometer. For this waveguide, let us calculate the number of symmetric and anti-symmetric modes at wavelength lambda naught is equal to 1 micrometer. First part, and second part, the waveguide thickness for waveguide to be single moded at lambda naught is equal to 1 micrometer. Well, so let us first solve the first part. I know for the number of modes what I should do, I should find out the value of V and divide it by pi by 2. So, I should calculate V over pi by 2. V over pi by 2 comes out to be 2d over lambda naught times square root of n1 square minus n2 square, because we know V is equal to 2 pi over lambda naught times d by 2 times square root of n1 square minus n2 square. So now I put the value of d, lambda naught, n1, n2 here, and I find out that this V over pi by 2 comes out to be 2.7527, which means that the number of modes should be an integer closest to but greater than this, and that is why the number of modes would be 3. Okay. If there are 3 modes, what modes are supported? Well, we start from 0. So, TE0, then TE1 and TE2, TE0, TE1 and TE2, and we see that all the even numbered modes are symmetric modes and odd numbered modes are anti-symmetric modes. That is how we got the solutions also. So here we have 2 even numbered modes and 1 odd numbered modes. So we have 2 symmetric modes and 1 anti-symmetric mode. Let us do the second part. Okay. Waveguide thickness for waveguide to be single moded. We had seen that if the waveguide thickness is 4 micrometer, then at lambda is equal to 1 micrometer, the waveguide supported 3 modes. Now, if I still want to operate at lambda naught is equal to 1 micrometer and want my waveguide to be single moded, then what should be the value of d? That is what I need to find out. So, I know again for single mode waveguide V should be less than pi by 2, which means 2 pi over lambda naught times d by 2 times square root of n1 square minus n2 square should be less than pi by 2, or d should be less than lambda naught divided by 2 square root of n1 square minus n2 square. Now, I just put the values of lambda naught and n1 n2. It gives me for all the values of d is smaller than 1.4531 micrometer, this waveguide would be single moded at lambda naught is equal to 1 micrometer. I can also find out the number of modes with wavelength. So, if I have a given waveguide, let us say defined by n1 is equal to 1.5, n2 is equal to 1.46 and d is equal to 4 micrometer, then if I change the wavelength, the number of modes will change. If I start from a wavelength which is say 2 micrometer, then there would be only one mode supported, let us say, and that would be TE0 mode. If I decrease the wavelength now gradually, then up to about little less than 1.4 micrometer, there would be only one mode supported, that is TE0 mode. As soon as I cross this, then TE1 mode will also come into the picture. So, here I will have TE0 and TE1 up to this point. This is about 0.9 micrometer. Okay. As I further decrease the wavelength below 0.9 micrometer, then TE2 mode will also come into picture. Now, here you will have TE0, TE1 and TE2 mode up to about, let us say it is little less than 0.7 micrometer, and then I will have TE3 mode and so on. So as I decrease the wavelength, okay, as I decrease the wavelength of operation in a given waveguide, the number of modes will change. So, I go to shorter wavelengths, I increase the number of modes. So, this is how I can find out how many modes would be supported okay, and how the number of modes will change with wavelength, how the number of modes will change with waveguide parameters. What still remains to find out is the values of beta, the values of propagation constant, the values of the modal fields, the expression for modal field, the field plots. So, for that what I need to do now, I have already got the value of beta, but approximate value of beta. This approximate value of beta I can refine by using numerical techniques. Okay, I can solve the transcendental equation by various numerical techniques, and I can find out the much more accurate value of beta, and from those values of beta I can find out the modal field. Okay. So, in the next lecture we would look into the modal fields, and before that in fact I would also like to define these transcendental equations in terms of normalized parameters. Okay. We have already defined one normalized parameter, which is normalized frequency V. I would like to also define a normalized parameter with respect to propagation constant. So, normalized propagation constant, and the idea of defining these normalized parameters is to have certain universal curves, certain universal solutions which do not depend upon waveguide parameters or the wavelength. So, in the next lecture we will extend all this analysis by using the normalized parameters, and then we will look into the modal fields also. Thank you.